So good morning, afternoon, and evening to everyone at anywhere. My talk is a bit different than the others at this workshop. Instead of designing a specific disaggregated systems, I want to talk about how to make it easier to prototype and evaluate work in this space. This is a joint work with Herjin, Jialin, and Antoni. To motivate the rest of my talk, let me start off by talking about why research on disaggregated systems and architectures is hard to evaluate. It turns out that there are multiple compounding challenges here. The first challenge is that work in this space often proposes to use radically different hardware architectures. For example, LogoOS implements memory disaggregation by turning local memory into a cache and removing address translation from the processor. A different example is NetDim. NetDim is a disaggregated system architecture integrates the NIC into a memory module. Such hardware is typically not available to researchers when they are working on these systems. The second challenge is that the performance and the behaviors of disaggregated systems heavily depend on complex interactions between different components. For example, in a conventional local memory system, memory accesses are not affected by other nodes. But with the disaggregated memory, completely unrelated node can significantly increase a node's memory latency. For example, there will be additional latency from network congestion. Such interactions will only show up in a full system end-to-end evaluation with realistic workloads. Finally, disaggregated systems are also naturally larger. While a conventional system design can typically be evaluated on one or a few machines, disaggregated systems generally aims for scale of at least one rank, reaching to complete data centers. Thus, meaningful evaluation should also reflect this scale. So, given these challenges, how has the prior work approached the evaluation? Let's discuss the different approaches about their disadvantages and advantages. The first approach is to emulate modified hardware using existing hardware. For example, emulating remote memory hardware through software page fault handlers. Emulation is flexible and often reasonably fast. However, emulators do not match the performance of the envisioned hardware. Typically, performance of a critical part of the emulation are much slower than they would be in hardware. Simulation addresses this by also modeling the performance characteristics of a component. However, due to the many components involved, most work only simulate part of the system, such as network or an individual hardware device. One useful feature is that many simulators are deterministic and independent of the hardware. So the evaluation results can easily be reproduced by other people. However, only simulating individual system components does not produce end-to-end results. In such case, it's likely to miss important behaviors of the system. If we have access to a simulator that covers all necessary components, simulations can enable full system evaluations as well. And there are a few instances of work in our domain taking this approach. However, in all cases, this requires significant one-off modification to and all needed pieces to the existing simulator. And the simulation result also requires laborious validation against real hardware to make sure that each component performs as required. To make matters worse, these simulations also scale very poorly with drastically increasing simulation times. All of that said, simulations are often the only way to enable full system performance evaluations for disaggregated system research. The goal of our work is to make end-to-end simulations of disaggregated systems easier. Let's dig into our approach for this. We argue that modularity is the key for addressing these challenges. To that end, we use our prior work, SimBricks, as a good starting point. SimBricks combines existing host, hardware, and network simulators for end-to-end system simulation. To achieve modular combination of simulators, SimBricks defines common interconnect interfaces such as PCIe and Ethernet. The component simulators run in separate processes. The component processes communicate with each other through message passing. We have shown that SimBricks is able to scale to more than 1,000 of components, and it can reproduce evaluation results in prior network system research. You can find more details of this in our SimCom paper. So, what changes are required when extending SimBricks for disaggregated systems? First off, many disaggregated systems will require additional system components that SimBricks does not include so far. For example, controllers for accessing remote memory or devices, as well as the corresponding network attached devices. SimBricks' modular approach enables simple way to integrate additional simulators. Users can add new simulators simply by adding an adapter to the simulator. The adapter implements a corresponding SimBricks protocol and interfaces to that simulator. SimBricks include component interfaces for PCIe and Ethernet. However, some components such as remote memory controller directly connected to a machine's memory bus. For such case, we extend SimBricks with an additional memory bus interface and show as on the right in the slide. And how to use our framework to simulate disaggregated systems? Here are the general steps. Users can directly pick up appropriate existing component simulators. For processors, GEMFAG and QEMU are available. For network simulator, NS3 and Tofino are available. For device and hardware, users can select NIC models or run hardware implementations by very later. If adding new simulator is a must, users can implement adapters for new simulators to connect to SimBricks interface. Users can also write Python configuration script to connect all components. Then after setting simulation parameters, users can start running the simulation. Now let me show you two examples of how we use our extended SimBricks to simulate previously proposed disaggregated systems. The first example is LogOS. LogOS proposes architecture and operating system support for memory disaggregation. In their evaluation, the authors emulate the DRAM cache with the virtual memory in software. LogOS also emulates disaggregated memory hardware with regular servers. In SimBricks, we instead simulate the hardware as designed. We add a hardware network controller simulator that forwards memory requests as Ethernet packet. And we connect this controller simulator to the host simulator through SimBricks memory interface. On the other side of the controller simulator, we connect it to the network simulator through the Ethernet interface. We also implement a remote memory simulator that also connects to the network simulator. Our second example is Mind. Mind moves dynamic memory management into the network switch to improve scalability of the system. let's now add some of this functionality to our previous example. We use a similar configuration to before, except we now have multiple memory nodes. However, this time we program the Tofino switch simulator to implement static memory management in switch to direct memory request packet to the right memory node. The Tofino switch is just programmed as usual in P4 language. We leave simulating the control plane for dynamic memory management as a future work. Our preliminary results show that with the 3 compute nodes and the 2 memory nodes, the simulation takes around 78 minutes to finish. With 20 compute nodes and 5 memory nodes, simulation costs around 112 minutes to run. Looking forward, we see 2 major challenges we plan to address. The first one is the high simulation times. High simulation times is preliminary due to individual bottleneck simulators, usually the host simulator, such as Gem5. To address these challenges, we are looking at parallelizing these bottleneck simulators using some of the ideas from SimBricks. I always want to speed up the simulation with hardware accelerations. The second big challenge is validation. Simulations results are only as good as the simulators and their parameters. With SimBricks, we hope to simplify validations through modularity. So eventually, users will only have to validate newly designed component simulators. Finally, there are some essential implementation pieces, such as adding CXL interfaces and adapters to SimBricks, as well as adding an essential RDMA NIC. To conclude, SimBricks enable end-to-end evaluations for disaggregated systems, even when physical test beds are not available. This is a preliminary work, so we are particularly looking forward for feedbacks from all of you. And the code is open source, so please have a look. Thank you. Any questions?
Have you compare your simulation system with like the real system, and do you know, like, since you are introducing like more components, do you know how accurate is your simulating system? Like you are introducing like memory bus and PCIe memory bus, and that the real setup might not be the same as like what you are in your simulator.
Okay. Thanks for your question. Currently we are at the stage that we show SimBricks is able to design the hardware simulator for the previous system work, and we haven't compare this with the real hardware, real system, and yeah, we in the future we will compare them. Yeah. No.
Paper, can you just like bring the code from their like published code and load into your simulator, or you have to like re-implement some components by your simulator?
Actually, in some system we can and we can just use their code for example, the mind they have before implementation in the terminal switch, and we can just use this code. But for local OS, for example, in local OS they use some emulation, and for such emulation we cannot directly use the code because we want to design some specific hardware, and this hardware cannot run this emulation code. Yeah, it's case by case.
Scalability. So your conclusion slide said you at least you aim to scale to hundreds of thousands of nodes. Just wondering if you have any idea how you would potentially achieve that. You said like FireSim based, or like how would you achieve this number?
Maybe I can take that question. So I mean, that number refers to the sort of original SimBricks paper where we did this for just regular network systems. So we have actually, I think the largest one we have run is 1,000 nodes, where basically the additional bit that we didn't talk about in this talk is that we basically have an additional building block, which are proxies that sort of translate these SimBricks channels across the network, right? So basically, in this case, you were running, I think, across around 25 machines in total, right? So you're literally at that point, you're running 1,000 instances of Gem5, 1,000 instances of like the NIC simulators that were connecting to, I think, about 25 top of rack switches, which in turn connected to a single core switch, right? So it's sort of basically just parallelism, right? Does that answer your question?
Very cool idea to modularize the simulation framework. And can we only simulate some part of the hardwares instead, like for others, we can use the real hardwares so that their part can be faster?
Another excellent question that we got the same question at SIGCOMM actually for the original paper. And so I think it depends basically on what you want to do. Right, so if you're just after functional simulation, right, if you don't care about the performance, then by all means you can do this. Right, the problem is like as soon as you throw real hardware into the mix, usually you sort of lose the ability to control the timing of like the software piece relative to the hardware piece. Right, so if you have a sort of RTL implementation, right, then you could sort of do things like use FireSim. It would use sort of hardware to accelerate the simulation, right? But in that case, with FireSim, for example, it's still a simulation, right? So you can still control how fast the clock on that circuit is running with respect to the other bits, right? But if you have a real piece of hardware, right, that's just going to run as fast as it's going to run, right? And typically, the relative performance of that would be much higher than whatever you're sort of simulating in software. That might be okay, but like usually it's sort of that's going to be a problem, right? It's going to throw things way off.